Okay, so next section, dual spaces. Let us recall something that we have already come across. Given vector spaces V and W over the same field F, we have defined this set hom V, W to be the set of all homomorphisms of V into W. Okay, so this is something we already know, we saw this. Now our aim here would be to show that this also is a vector space over this field of scalars F. For that we will need to introduce an addition and multiplication by scalars. So those are the things we are going to do now. We want to turn this set into a vector space over F. Okay, so that means first of all we will define addition and show that the set is the group with respect to that addition. But before we do that, we actually have to make sure that this set is a non-empty set, because otherwise if it is the empty set, then everything stops there itself. So we now show that in any case, no matter what these spaces V and W are, there is at least one element that will always be in this set. So we are going to define a function which we are denoting by 0 from V into W by this. V0 is defined to be equal to 0. Okay, so note carefully that we are using the same symbol to denote different things. First of all, we are calling a function 0. Fine, and the definition of the function is this, where this small v of course is coming from the domain, and the image of small v under this function is defined to be equal to 0, and this 0 is the 0 vector in the space W. Okay, but in spite of using the same symbol, you can of course understand which one is which from the use and from the context. Now our aim now, first of all, is to show that this 0 function is an element in this set. That means we have to show that this function is a homomorphism from V into W. To do that, we proceed like how we usually do. For V1 and V2 belonging to V and a scalar alpha in the field, we have So we need to show two things here. This zero function respects addition, vector addition, and zero function also respects scalar multiplication or multiplication by scalar. Once we show these two things, that will tell us that this zero function is an element in this set. So let us see. So we take the sum of these two vectors and apply the zero function on that. By the definition of the zero function, this is nothing but 0, and this 0 is of course the zero vector in W, which can be written as 0 plus 0. And these zeros then can be conveniently written like this. In place of 0 we can 0 is the zero image of V1, where this is our zero function. Similarly, this 0 is the zero image of V2. So we see that the zero function actually respects addition. We start with two vectors from the domain and take their sum. We end up with a sum in the second set, in the codomain or range, whatever you may want to call it, where the images are involved. And just like that, if we consider this multiple of V1 by the scalar alpha and apply the zero function on it, by definition again we get the zero vector in W, which itself, using elementary properties of vector spaces, can be written as alpha 0. And in place of 0 here, you can write the zero image of V1. So the zero function not only respects vector addition, but it also respects scalar multiplication. So this tells us that the zero function is in this set, and consequently this is a non-empty set. This implies zero belongs to hom V comma W. Consequently, this is a non-empty set. Now we define addition. For two homomorphisms S and T, we define a function S plus, keep in mind that this S and T, because they are coming from this set, are, each one of them is a homomorphism from V into W. Now we are going to define a function S plus T from V to W by this formula. The S plus T image of any vector V from the domain is defined to be equal to the S image of V plus the T image of V. And this plus, you can of course understand, is the plus in vector addition in the target space W. Now, okay, now just like what we did with the zero function, we want to now do it for this new function S plus T. We want to again show that this S plus T is also an element in hom V comma W. So we have instead of again and again writing, because we will have to do it many times, okay. So instead of writing that v1 and v2 are vectors in V and alpha is a scalar in F, we just assume that that is the case, at least with these calculations. So like we have to again carry out these calculations now for the function s plus t. So here we will not again mention what v1, v2 and alpha are. So we directly write, we have v1 plus v2 s plus t. So this is the s plus t image of the vector v1 plus v2. And let us see now how s plus t, just like the zero function, respects addition, and then of course scalar multiplication. At each step we have to carefully observe why the step is true. I mean how it's a consequence or how it is coming from the previous step. It's very easy to lose track of what we are doing in these calculations and do something unknowingly, and that's just it. It will not usually lead you to any error, but you will just don't understand. You will end up not understanding why you wrote something. So be carefully, first of all, what we are going to do. First of all, because this is the s plus t image of some vector, we are going to use the definition of s plus t, because that's what we have, right? So that means this is the s image of v1 plus v2. In this step we ignore the fact for the moment that v1 plus v2 itself is a sum. We just consider it as a single vector. Okay, so this is where we just have applied what the meaning of s plus t. We have just simply applied the definition. Now we are going to use the fact that s and t are homomorphisms, and so each one of them respects addition, and that is why we can write v1s plus v2s. This is equal to this. Similarly, this one is v1t plus v2t. Why am I not writing any brackets or anything and still there is no problem? That is because this final sum is happening in the space W, which is an abelian group with respect to its own addition, and that addition you see here. So we have associative law, general associative law is true in any group, so there is no need to write brackets. And because of the fact again that this is not just any group but an abelian group, we can change the order of these terms. So changing the orders, we can write things like this. And now for our own convenience, we can in fact use bracket to in fact give us a hint about what we are going to write next. So now if you look at the definition of s plus t again, if you go back to that, then this is the s plus t image of v1, this much, just like that. This one is the s plus t image of v2. So that's how we get the fact that s plus t in fact is also a function which respects vector addition. And what about this alpha v1 s plus t? Again, first of all, we apply the definition of s plus t. So this is the s image of alpha v1 plus the t image of alpha v1. Then again use the fact that s and t are homomorphisms. So this is alpha times the s image of v1 plus this is alpha times the s image of the T image of V1. Now in the next step we can write something like this: alpha times the S image of V1 plus the T image of V1. And do you see why? That is because this type of calculation is actually an axiom in the vector space W, where actually what we have used here in this step is just simply this thing. You have alpha in F, and say you have two vectors W1 and W2 in your second space W. Then alpha W1 plus alpha W2 is equal to alpha times W1 plus W2. That's what we have done in this, we have used in this step. And now there is one more step. You again use the definition of S plus T here. So in this final step we write alpha times the S plus T image of V1. So you see that S plus T also respects scalar multiplication. Hence S plus T belongs to the set of homomorphisms of V into W. So the sum we have defined at least again leads us to an element inside the set itself. So the set is the set home is closed with respect to this new operation, the sum. Okay. Now we need to next prove the associative law. For the associative law, however, we will need we will not need three vectors, but we will need three homomorphisms. Fine. For S, T and U, belonging to this, we have the arbitrary vector that we will need from the domain space V is, let us take that to be V1 itself. So what we are now going to do, we are going to look at the effect of this function on V1. First of all, you apply the definition of this outer sum. So this is equal to the S plus T image of V1 plus the U image of V1. Then again you apply the definition of this sum. You get the S image of V1 plus the T image of V1 plus the U image of V1. But this expression is a sum in the space W, where the sum that you see here is the vector addition in W, which we already know is associative. So this thing we can write as V1S plus V1T plus V1U. If you really want to get down into the details and show everything, then you have to write the justification of each step beside the step, which however we are not going to do because you can clearly see what we are doing in each step. So this equals v1s plus, now we go in the other direction. Now we combine things together and again use the definition of these plus. So the thing you see inside within the parenthesis, that is the t plus u image of v1. Then again once more using the definition of sum, this is the s plus t plus u image of v1. Now you can see that this v1 that we have chosen from the space V is an arbitrary vector. So that means these two functions s plus t plus u and s plus t plus u actually give us the same image for a given input. So as functions they are equal, thus so that means the addition we have defined has now been shown to be associative also. Next, we see what happens if we apply 0 plus, let's use s, on this arbitrary vector v1 from capital V. By the definition, you see we are at every in many places we are tempted to use or write some things which seem very natural to us. For example, you see here 0 plus s, we are tempted to write simply s, but that is something we need to first of all show. Here 0 is not an ordinary number 0, it will be equal to s, but that's what we are now going to show, and that is why in fact we are using this symbol 0 to denote the 0 function. It behaves like the ordinary number 0 with respect to all these things. So the only thing we can now do is apply the definition of sum. So this will be the 0 function image of v1 plus the s image of v1. Now by the definition of the 0 function itself, this is equal to the 0 element of the space W plus v1s. Now you can write v1s, because we know what happens when we add the 0 vector in a space to any other vector, we get that any other vector, and we can continue this calculation like this also, v1s plus v10, so that is equal to v1s plus 0. Hence 0 plus s equal to s equal to s plus 0. So that 0 function, which first of all we showed is an element in this, actually acts as an additive identity. Additive identity means it acts as an identity with respect to this addition that we have defined on home v comma w. So to prove that it's a group now with respect to this addition, the thing we are left to prove is that every element has an inverse. So for that our any element is s. Next, I think I need ink. Okay, next we are going to define a function which will be an inverse of s, and because of that reason we use a symbol like this minus s, which you just have to remember is a name given to a function. This minus by itself does not have any meaning. So it's a function from v to w by this formula. V minus s. While defining these functions, we have been using v, okay, where we understand that this v is coming from the domain. We need not use v1 here. This is the inverse of the vector vs. Note that once you apply your s, and we are in fact using the function s here in this definition, you just notice that thing, because here we are considering the image of the vector v under the function s, and then we are not simply considering the image but rather its negative, its additive inverse in the space w. There are other issues here also which are actually extremely easy to see that they are actually not issues at all. The thing is that you see, we defined the zero function, then we defined sum of two homomorphisms, that is also a function we defined. Now we are defining another function. So in all these definitions you actually have to make sure that these are well defined functions, okay. For every element in the domain it gives us a unique element in the codomain or range, okay. So those things here for these functions that we have seen so far are so easily true that I have not mentioned that at all, but it is there, okay. Well definedness should be there, otherwise if we don't have a well defined function, that's it, you don't that is useless. So like that, this is also well defined. I am not going to say anything more on this, how it is well defined. So let us now instead see that this, if you add this minus s with this plus s using our newly defined addition, then you are going to get this zero function. Now v1 s plus minus s, we are being careful, we are not simply confusingly writing s minus s. It is written, I mean the meaning of s minus s is just this, but we are keeping these two functions separate and we are showing the fact that actually we are considering their sum. So this is equal to, by the definition of our sum, v1s plus v1 minus s. This is equal to v1s. Now you can use the definition of our minus s. So this is minus v1s. Note carefully that the brackets are being used here in a very specific manner. This means the image of v1 under the function minus s, and this means the negative of the image of v1 under the function s. Those actually are two different things, but because of the way we have defined these things, the meaning of this is just this, and this is simply 0, and this 0 is what? This is the zero vector in W, and that itself can be written as the zero image of v1, and this 0 here is the function 0, and this of course can also be written changing the order, plus v1s, so that is v1. Since we are writing these things in details, let's just write one more line, and that is equal to v1 minus s plus s. Okay, here you don't have to use any additional bracket because minus s is already separate. So now you combine these things. The image of v1 under s plus minus s is equal to the image of v1 under the 0 function, which is equal to the image of v1 under minus s plus s, and v1 is an arbitrary vector in our domain space. So that means these three functions are equal. Thus, we have s plus minus s equal to 0 equal to minus s plus s. So if any element s in the home set has an inverse minus s. Thus, this is a group under the operation plus defined on it above. But this is not just any group, it's an abelian group. Also, v1 s plus t, where you of course understand that t is that t that we considered before. So these are two elements coming from that home set. v1s plus v1t, but because addition, vector addition in the space W is a commutative operation, so we can write v1t plus v1s, that is equal to v1 t plus s, i.e. s plus t equal to t plus s. So this is abelian. When we write this is abelian, we mean of course with respect to this addition. Okay, so we have shown that our set of homomorphisms is an abelian group with respect to an addition that has been defined very naturally. I mean, as naturally as possible, using the natural definition of sum of two functions, when that makes sense. So next we want to define scalar multiplication on this set. We want to take an element in this set, take a scalar from the underlying field, which of course is there in the background, and somehow multiply them, and we now want to define what that multiplication means. For s belonging to, once more let's just write where s is coming from, s belonging to this and alpha belonging to the field, we define alpha s. So like before, we want alpha s to be again an element here. That means this alpha s should be a function from V into W. But what is its definition? Its definition is this: V alpha S. That means the alpha S image of V, where this small v is coming from capital V, the domain space, is equal to alpha times Vs. Things may look somewhat quite confusing. Okay, don't get confused. This alpha S is the function we are defining. It's the image of V under this function is defined to be the scalar multiplication of alpha and the image of V under the original function S. And like before, you can show that this function is also a well-defined function. For a given V, there is a unique image in W. And you have to actually make sure that this is in fact a vector in W. All those things are included in the statement that this function is well defined. So I am not going into that. I leave that to you. If you have some confusion, in fact you should go. If you never went through this type of things, you should actually think step by step how this function alpha S is a well defined function from V to W. Now instead, what we now next of course we are going to show is that this alpha S is again here. So alpha S now has to be shown to respect addition and scalar multiplication. So we just start the calculation. We have, but wait, now before we do the calculation, because we said that we are going to use V1, V2 and alpha in this type of calculations, so that alpha and this alpha will clash. So because of that, in order to distinguish between those two scalars, let us denote this by beta. Beta S. Okay, now what do we have? In the first one, in trying to show that this one will respect addition, there is no other scalar involved, so it's just simply V1 plus V2. On this we are applying the function beta S. So by the definition of this, by this definition, this is beta times the S image of V1 plus V2. Now, because S is a homomorphism, so S respects addition, that is why the thing inside is V1S plus V2S. Now, we are doing this calculation in this second space W, and in the second space W, in place of this, we can write another expression, which is one of the vector space axioms in W. And that thing is equal to beta times V1S plus beta times V2S. And now you again look at this definition. Using this definition, we can write the first term as the beta S image of V1 and the second term as the beta S image of V2. So beta S as a function respects addition. It distributes itself over the addition. Okay, keeping the addition and addition again. We start off with an addition in the domain space and we get an addition in the range space. And it's not over yet. Yeah, here there are two scalars involved, right? So we have to be extra careful. We are considering the multiplication of v1 by the scalar alpha, and on that we are applying the function beta s. First of all, the definition of beta s has to be written. Using that definition, what we have is this: beta comes outside, and on alpha v1, on this vector, we are applying the homomorphism s. Okay, and now again, just like here, we use the fact that s is a homomorphism, so it respects addition. So now s is going to respect scalar multiplication. So we can write like this. Okay. Now again, one of the vector space axioms in the space W tells us that in this situation, keeping in mind that this beta and alpha are after all scalars coming from the underlying field, and this v1s is itself a vector in W, we can write in place of this thing: beta alpha v1s. Now in the next step, what we do, we use the fact that this product, where is this product being carried out? It's being carried out in the field, because beta and alpha are scalars, and we know that in a field is a commutative ring. So in place of beta alpha, we can write alpha beta. And now what we will do, we will do this step in reverse. Most of what we are doing is straightforward, but there are some subtleties here and there. So in the next step, we can write alpha beta v1s. So in this step and in this step, actually we are using the same axiom but in the opposite direction. Now what we do, we here inside these square brackets, we use the definition of beta s once again and write this equal to the beta s image of v1. So now you look at the final thing and the initial thing of this sequence of steps. So applying beta s on alpha v1 is the same as applying beta s on v1 and then multiplying that with alpha. So that means beta s respects scalar multiplication also, just like it respects vector addition. This shows that beta s is also a homomorphism from V into W. So far we have just simply shown that beta s is in W. Is in this home set. But note that this is not enough. We still have to show those 4 vector space axioms which come last in the definition of a vector space. So we now look at them, each one of them one by one. So for that, what are the ingredients that we will need? We are going to need, we will see what we need as we as we start the calculation. Our arbitrary vector from capital V is we are going to keep it V1. Okay. Now alpha S plus beta S. We are keeping S fixed. That means our vector in home V comma W, although we cannot call it vector, we still haven't shown that it's a vector space, but I'm just simply saying the vector in home V comma W has been chosen to be a single one, and the scalars we are taking from the underlying field to be two possibly different scalars, and we are applying this combination on V1. So first, by the definition of our addition, this is V1 alpha S plus V1 beta S. Next, in the next step, we of course have to use our definition of scalar multiplication. So this one will be alpha times V1S plus beta times V1S, using the definition of alpha S and beta S. Now again, in the vector space W, this thing, because V1S and V1S same thing, this is a vector in W, this thing can be written as alpha plus beta times V1S. Now again you apply the definition of scalar multiplication, and doing that you can write this as the image of V1 under the function alpha plus beta times S, where here of course you understand that this is just like this product of these functions and some scalar. So because our small v1 is an arbitrary vector in capital V, so we get this. This is one thing. Then next, in the next calculation we are going to change the function but keep the scalar, we are going to take a single scalar but two possibly different functions. So alpha s plus alpha t. So similarly, going through all the things, first we have the alpha s image of v1 plus the alpha t image of v1. Using the definitions of these alpha s and alpha t, we next get alpha v1s plus alpha v1t. Now in the vector space W, this thing becomes alpha times v1s plus v1t. Okay, and this implies, this equals v1 s plus t. And here what we have done, we have used the definition of s plus t, and once again using the definition of scalar multiplication, this thing is the image of v1 under the function alpha times s plus t. i.e. alpha s plus alpha t is equal to alpha times s plus t. So this is one other axiom that we needed to verify. Two more are left. Next, in the next one, two scalars are involved. Although the things are extremely straightforward, then there is usually no twist in unusual twists in these calculations, but you have to carefully interpret which thing is what. Three types of objects are involved in these calculations. One, of course, the scalars coming from the underlying field, and another type of object is the vectors coming from the space domain space V, also from the codomain space W, and the final type of object are the functions, the homomorphisms themselves, S and T. So you don't confuse among these things. So here we need two scalars, alpha and beta, and one homomorphism S. So what we are going to first of all consider is the effect of this function alpha times beta S on V1. First of all, by defining our by using our definition of scalar multiplication, this is alpha times the image of V1 under beta S. Again, using that definition once more, this is beta times V1s. Now, using one of the axioms in the vector space W, this thing is equal to, because alpha and beta are of course scalars and this V1s is a vector in W, this thing is equal to alpha beta times V1s. Once more, using the definition of scalar multiplication, this thing is equal to the image of V1 under the function alpha beta times S, i.e. alpha times beta S is equal to alpha beta times S. So one more axiom needs to be verified. Then we will have the right to say that our home is a vector space. Finally, we are going to calculate this, the effect of 1s on V1, where you should of course understand this, that this 1 is the multiplicative identity of the underlying field, the scalar 1. So by the definition of this 1s, this is 1 times V1s, but because V1s is a vector in W, so using the if I say so, you will understand the last axiom in the vector space W, this thing is equal to V1s itself, i.e. 1s is equal to s. Do you see one thing, that the way these things behave are exactly like some other things with which we are familiar, that is ordinary numbers. And that fact itself prompts us to adopt these notations, because it becomes easier to remember how these things behave when we use the same notation. For example, usually when you see something like this 1x, you are tempted to write x. In this case, of course, 1 is not the number 1, but it's the multiplicative identity of the underlying field of scalars, which may actually be different from the integer 1. It depends on the field, but still it behaves like ordinary 1 even in this situation also. I mean, the way we have defined scalar multiplication, we are no longer multiplying, say, any vector, or I mean, for example, we are considering this space. No, V is a vector space over F. So we are not multiplying any vector from V by 1 here, but we are in fact multiplying something else, a function, by 1. But the way the multiplication has been defined, it ultimately leads us to this very natural looking equation, and that is why it makes sense to use the symbol 1, because it retains all these properties of the ordinary integer 1. It helps us remember the things better, and that's why the 0 function is also written as 0, using the same symbol that we use for the integer 0. So that is the advantage. The disadvantage is that sometimes we may get lost and get carried away with these things so much that we may forget to properly interpret what they represent or what they actually are. So you just have to understand that, and you can also understand why these type of notations are justified. The same thing can also be said, for example, what is the justification when, say, we write every time we encounter an abelian group, we write plus for the binary operation, although of course different abelian groups have different binary operations. So why do we use the same symbol plus for them? Because all those operations behave like ordinary addition of numbers. Okay, so that's why we use that, because you can understand that it becomes cumbersome and nearly impossible to, again, I mean, in each case come up with some new symbol which somehow denotes the operation. It becomes cumbersome, and more importantly, it becomes unnecessary. So that is why we use this type of things. And in the multiplicative notation of writing things in a group, in a general group, we do not use any symbol for the binary operation. So that saves us from writing things unnecessarily. When you write two elements one after another in a sort of juxtaposition, you just simply assume that the binary operation is there in between these two things. So anyway, we have now managed to show what. Let's just write the conclusion. It's given here in the form of a lemma. And the lemma is just this: our set home v comma w is a vector space over F under the operations described above, Herstein writes, but let me write defined above, because we did not just simply describe things, We actually define the things and then we showed all the things. Okay. Now a final word about these things. Note that in spite of doing so much with this set and those two operations, so far we don't really know whether there is any element in this home set apart from that zero function, because in all these axioms that we worked so hard to verify, all the existence of those functions, for example, there exists a minus s for every s and things like that, and say you consider s and t, then there exists a function s plus t which behaves in this way, that way. There exists a function alpha s. All these existences are conditional existences, in the sense that when you assume that something exists in home v comma w, based on that assumption something else, these things exist. The only thing that we have actually shown exists so far in home v comma w is the zero function, and that also proves the fact that this is a non-empty set. But we don't yet know whether there is something else also in this. If there is nothing else, then this will be an extremely boring situation and all our hard labor will go in vain. If this vector space turns out to be the zero space where there is a single object, a zero dimensional space. But we will see in the next result that actually there are many things, and in fact we are going to show that if v and w are finite dimensional vector spaces, say v has dimension n over f and w has dimension m over f, then this is also a finite dimensional vector space and its dimension over f is the product of these two dimensions n m. Okay, so this we will show in the next result, and that of course I will do in the next video. But before we end this video, let me just say something else about this home set. And we will no longer call it simply a set space, because we have just shown that it's a space of homomorphisms which also have another name with which you are of course already familiar from elsewhere. That is, these vector space homomorphisms are also called linear transformations. Now, there are two special cases of this vector space. One of them is this, which we will consider in this section. Recall that if V is a vector space over F, then F itself can also be regarded as a vector space over F. This is something we already saw, we have already seen. So in place of W, you can in fact consider the field of scalars F itself. Here also we get a space of homomorphisms or linear transformations, and these linear transformations take one vector as input and gives you a scalar as output. This type of functions you have already seen. For example, temperature of a particular point in a place is such a function. A particular point is given by its position vector, and you can and the temperature is a real number. If you want, you can bring in time also, say the temperature of an event or something like that. So the elements in this are, they also have a and yet more special name, linear functionals. And there is one more special case that is of interest, is when the two spaces V and W actually are the same. When you consider the vector space homomorphisms or linear transformations of a space V into itself. These sometimes are also called as, the elements in it, linear operators. Linear operators arise here and there in almost all places. If you means you already have gone through differential equations, there you came across linear differential operators and things like that. Now, when V is finite dimensional, then the study of this space is your linear algebra. And when, of course, you can also consider this space when V is infinite dimensional, but when V is infinite dimensional, this space usually is so large that in some sense it's not very suitable to study this using only algebra. Something else is needed, some topological structure which somehow behaves very well with the algebraic structure, and there you get those things, Banach spaces, Hilbert spaces in functional analysis. So we will see all these things, okay, and we will see the next result which tells us the exact dimension of this space when the original two spaces have their dimensions given. But I am ending the things here itself for this video. If you want to comment anything on these things, you can of course use the comment section below, or you can mail me at my usual address. The link will be there in the description, and you are being requested to go through the description, because there I write what we have done in this video and what we are going to do next. Next means tomorrow again we have, and what is the thing that we did on previous Saturday? Is it Lie algebra exercises or Gallian's group theory? I can't remember exactly. If it was Lie's algebra exercises that we solved, then I am going to do Gallian ring theory. But if it is Gallian group theory exercises that we solved, then I am of course going to do Lie, because Gallian group is something that we already did, I think, so far I remember. So we will see, it will be there written in the description. And Sunday, of course, we again have our real analysis, where we are going to go further into the theory of infinite series. Well, so with that, it will be all for tonight. So see you tomorrow with whatever we have to do, either Lie or Gallian, we will see. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.